All right. Hello and welcome everybody to Technically Speaking, Season 3, Episode 1. And although we are in the second month of the year, this is the first episode of Technically Speaking for 2024. My name is Brandon Burton. I'll be your host today for Technically Speaking as we explore the world of drying chambers and classes of water. A couple of topics that I think are very foundational to the water damage mitigation subject area and setting up proper job scope and drawing plans, etc. So we're going to spend the entire day today just digging into these two topics. Before we do, though, a couple of housekeeping things that we like to start with. First, just making sure that everybody's aware that we do a significant Q&A session at the end of every Technically Speaking episode. And the way that we manage those is through the Q&A tool in Zoom. So if you're not familiar with the Q&A tool, please do take a moment to find that. It's a little like an icon there that you'll find in your menu bar, and not the chat feature. Make sure you find the Q&A, which is two little speech bubbles, where the chat feature is a single little speech bubble. Those questions, if you log those through the presentation today, I will field those questions at the end of today's session. And no questions off limits as long as it's somewhere around the restoration industry at large. It can be anything to do with water, fire, remediation, standards, et cetera, et cetera. Any questions that you have, I'll do my very best to address those. And if there are questions that I don't know, then we'll just log those for potentially a future conversation with Technically Speaking. So having said that, let's go ahead and jump right into it. So again, my name is Brandon Burton, and I come to you with Technically Speaking as a series, really as a forum to get into some of the deeper technical conversations in our industry. I'm a huge supporter of really embracing the professionalism of our industry and really understanding the core of the science behind what we do. And that always comes through in everything that I like to participate in industry. So I first want to start off by just saying thank you for participating in Technically Speaking and allowing me the forum to address topics like this. So I thoroughly enjoy doing it, and your support is absolutely amazing in that regard. So thank you. So with that, let's jump into it. First thing I want to do today is I want to attack just the conversation of class of water from a technical standpoint and talk a little bit about the ANSI IICRC S500 and some of the guidance it gives us about what this tool called class of water really is and what it represents, and talk about some of what I see in industry as great interpretation of that language and not so great interpretation of that language. I think class is one of those things that gets misunderstood and misapplied a lot. And if it's not used the way it's intended, I think it can have some very negative results in the impact on a project. So it's really critical to come at this tool and really understand what it's intended for and how it's technically defined. So with that said, the first thing I want to do is just go through some terminology with class and define what it represents. First of all, the purpose of class, if you look in your S500 standard, is that it's an element of the initial humidity control, right? So I'm going to underline and stress this word initial here in this terminology. This comes right out of the S500, but it's a part of the initial humidity control. And I can't overstate the significance of the word initial. And I'm going to stand this up a couple of different ways, but I think it's really critical that we understand that the only reason why a class of water exists is so that we can take an initial approach to the establishment of control over an environment. And once we've established that control, or at least made an attempt to establish that control, there is no longer a mathematical formula for what we need for drying equipment. Everything that happens from that point forward is going to be based on our instrumentation, what we see happening in the environment, and comparing that against what we expect or what we require, and adjusting accordingly. And I'll talk a little bit more about that as we dig deeper into this topic. But that word initial is critical. It is an initial guess. It is an initial hypothesis, right? Just to throw a dart on the board and find out how far off our aim is, or if it's off at all. From there, the next thing I want to define is the core behind class is that it helps us approach an estimated evaporation load. All right, so what does that mean? So based on some of the other things we see down below this, how much wet surface area there is, of those wet surfaces, what is the permeance and porosity of those materials? How many holes do they have in it and open air spaces to hold on to water? And are any of those materials low evaporation materials that hold on to water very tightly and let go of it very slowly? Based on all of that, class is designed to give us a rough guesstimate for the rate at which water will be leaving materials when we first begin the drying process, that evaporation load, right? So over a given area that we're dealing with within that environment, how much water can I expect to see be entering the air every minute, every hour, et cetera? And therefore, how much hardware do I need, or what systems do I need to compensate for that, right? So for every drop of water being added to the air, I need to have a means for removing that water from the air, whether that be through dehumidification or ventilation or any other means, right? So it's the estimate of the amount in, so that I can then predict, at least initially, how much I need to pull out. Now, the evaporation load is based on a couple of different criteria. The first of that criteria is, again, how much wet surface area are we dealing with, right? And it's an approximate, it doesn't have to be exact, because the effort of class is an approximation anyway. But what is the approximate wet surface area that I'm dealing with? Of that wet surface area, what is the, number two, permeance and porosity of those materials? And then finally, if I don't have high permeance and high porosity, are all of those surfaces low permeance surfaces, low evaporation surfaces, surfaces where the water is hidden, trapped, or bound, or otherwise difficult to remove? These criteria, these three, all set up my class of water. And generally speaking, we reserve those classes by the following definition. A class 1 water damage is when we're dealing with a very small affected area within a larger open space. A class 2 is dealing with a significant amount of wet area in a larger open space. And class 3 is dealing with predominantly the majority of those surfaces within a large open space. And then class 4 being the reservation for regardless of surface area, if those surfaces are all low evaporation assemblies, right? Now, a couple of things I want to point out before we move off of this initial conversation about class. First and foremost, again, the key here is initial, right? We don't apply a class to a job and then manage the entire job just based on that single classification. We apply a class to a job so that we can estimate the equipment necessary to manage that evaporation load. So that's point 1 on the timeline. From that point forward in the timeline, all of my adjustments are going to be based on the readings I'm obtaining with my instrumentation. Am I making progress in my building materials? If I am making progress, then the drying plan is effective, right? If we're making reasonable progress, then that estimate was accurate. If we are not making reasonable progress on our building materials, then an adjustment is necessary. And it's not a class that I will use to justify that adjustment or to reason with that adjustment. It is the environment. It's my atmospherics. It's my temperatures, my humidities. It's my materials, their porosity. Where is the moisture? It's the absorption. Where is the water that's not making progress? And is that hidden from the environment that I'm trying to apply, right? It's all about my instrumentation and my investigation into the environment from that point forward, okay? So that's kind of a high-level overview of class. And we're going to now do the same thing with category, or not category rather, but drying chambers. And then we're going to kind of bring the two together and go through a couple of scenarios and kind of apply that logic as we move forward with the discussion. And as I say that, I just want to shout out a quick thank you to Chris, being the first one to drop a question into the Q&A. Thank you for that, Chris. I'm going to address all of the questions in a Q&A session at the end, but I want you to log them now. So thank you for doing that, Chris. If you have a question as I go through, open up that Q&A tool, drop that question in there, and then we'll go back through all of those questions in the Q&A once we wrap up with the initial technical side. All right, so the next step here is I want to kind of dive in and have a similar discussion with drying chamber. So I want to define both of these terms and make sure these terms are stood up before we get into the application. The second phrase here, or phraseology that we're going to discuss, is this phrase called drying chamber. All right. First of all, the first thing I want to point out is that if you go into the S500 and you take a look at drying chamber and you look it up in the important definitions, you're going to find that drying chamber has a really simple definition. It says see drying environment. Right. So in the S500, we don't actually call it drying chamber. We call it a drying environment. And there can be multiple drying environments. A drying environment is a controlled environment within my project where I can create existing or temporary barriers to isolate that environment that I'm trying to control. And again, there can be multiple separate drying environments within a single project. Each environment can have a different category or class, right? So the assignment of this class that we discussed a moment ago is an independent assignment that occurs not by room, all right, not by area in a room, but it is an assignment that occurs by drying environment, also known as drying chamber, right? Now, I'm going to use the phrase drying chamber through the presentation today because drying chamber is what we very commonly refer to these as, especially as I go through the applications and the scenarios. But I do want to give you that heads up that if you go into the S500 and you're trying to look up the language that discusses how to establish or manage a drying chamber, you're not going to do a word search and find drying chamber anywhere in the document except one place, and that's going to be in the definition section. And what it's going to tell you is see drying environment. So then search drying environment, and you'll see a number of references to drying environment. One of those references, by the way, is in section 12.5.3 of the S500. And to me, it's one of the most important references to a drying environment or drying chamber. It's in the same section where air movement is discussed and how to control airflow in a drying environment. It's where you'll find the formula for air movers, right? For how many air movers are going to be placed, and even the alternate method of using linear feet along a wall. All of that language is in that same section 12.5.3. It's a very critical section of the S500. But one of the things it says there in relation to a drying environment is that it's a requirement of the standard of care. So it's a should that in a drying environment, air is circulated throughout that drying environment to include interstitial spaces. And this is one of the keys that I want to call out in a drying environment or a drying chamber, is that a lot of us look at a room and we see, the drywall, the sheetrock, or the wall paneling. And that, because our mind sees that as the barrier to what we can see, very commonly that also becomes the barrier to our drying environments, right? And we manage air inside that room, we manage humidity inside that room, temperature inside that room. But what we fail to see, and oftentimes, is that there are many, many micro environments that surround that chamber or that space that we have to consider whether or not they also need to be included in this statement that we see in 12.5.3. Right? I need to circulate air throughout the entire area where wet surfaces exist. And if my wall plates are wet, my wall insulation is wet, the wall behind my cabinetry is wet, the surfaces underneath my hardwood floor are wet. These are all interstitial spaces and cavities and voids where if there is a wet surface present, air needs to circulate into and out of those spaces so that my drying chamber, my drying environment, that air movement becomes that communication, that transportation, that blender that ensures that all of that moisture travels out of those spaces into the mechanical systems I'm using for humidity control or the ventilation, whatever it is that I'm doing. And that air is being subsequently replaced by the air that is actually going to promote the drying process, right? And we really have to think almost like we've got X-ray vision when we look at how we establish these environments and establish control over these environments. And if we don't look beyond those materials that we can see into the assemblies that are actually affected, then we'll overlook a lot of those problem areas. Even our instruments are really set up to fail in this regard because typically we use a lot of instrumentation that's not really capable by itself, unless you really understand how to use it, that's capable of looking beyond the surface, right? A non-invasive instrument, I'll give you just as a case in point. Typically when we take these meters that don't have pins, they just have little pads on the back, and we place that along a surface, those instruments have a very limited depth that they can measure with any amount of accuracy. And typically, I treat that limitation at about a half an inch. And I don't really trust anything that a non-invasive instrument gives me beyond a half an inch without a lot more concerted information and thinking about what the instrument is actually telling me. We covered that in a couple of episodes over the last couple of seasons, really getting into the limitations of instruments. And if you haven't seen those episodes where we dove really deep into the instrumentation, I highly, highly encourage that you do, especially if you're a field operator and you use instrumentation, because your eyes are only as good as your knowledge of the limitation of those instruments, right? And if you put too much faith in that instrumentation without truly knowing their limits, you're going to go into a job blind. And I really can't stress that hard enough. They're a necessary tool. They're an important tool. They're a critical tool. They're a very useful tool, but they're only as useful as your knowledge of their limitations, right? All right. So anyway, I'll jump off of that soapbox for a minute. So kind of in review on drying chamber, it's important to understand that, first of all, if you're looking for it in the S500, I want you to note that you're looking for drying environment in the S500. That's the language, the vernacular that's in the S500. And know that we establish these by finding the totality of the water's migration. Where is the edge? If that edge is inside a chamber, or excuse me, inside a cavity or inside of an assembly, then I have to extend my drying environment, extend my drying chamber to include that migration into that assembly or into that wall cavity or that interstitial space or void. And then once I've established that chamber, it's uber critical that I then establish air movement, air flow that is going to reach all of those wet surfaces and ensure that that evaporating moisture can be transported, right? It can be carried. And that's really what air movement is. At the heart of a drying process in your drying plan, the purpose of air movement is to provide transportation. And if I don't provide any transportation to that wall cavity, the water vapor in that cavity is not going to move. Those materials are not going to dry. It's going to become wet and stagnant in an environment where we're artificially warm from our drying equipment. And warm, stagnant, and wet, especially in a dark wall cavity, is a really, really bad recipe. So anyway, those are the terms that I wanted to define. And now that we have those defined, let's go ahead and jump into some scenario discussion. So I'm going to start off really simple with this, just taking a really basic floor plan and kind of talk through a little bit on both class and drying chamber management. The first thing I want to do is just to start with the drying chamber management discussion. One of the things that I love to do, and if this isn't something that you're pinging me for, please do. But I love to provide drying technical support and just receive from you kind of some scenarios that you're seeing in the field where maybe you've got a question on interpretation of the S500, or maybe you've got a particular challenge with a client in a disagreement over determination that you've made on a particular project and you want some feedback on that. I love receiving those types of inquiries for lots and lots of different reasons, not the least of which is it really helps me stay plugged in with some of the challenges that you're facing in the field. And as the standards chair for IICRC, I really like staying plugged into that. It's been, I've spent a good amount of time in the field myself, but I'll be honest with you, it's been a bit, right? And that's part of how I stay connected with that. So please do use me for that. But the reason I bring that up is because one of the things that I get a lot of questions about is about the establishment of a drying chamber. Am I establishing my chambers correctly, right? Is this one chamber? Is it two chambers? Is it three chambers? And what you have to look at to understand how many chambers a given area really should be is the ease at which you can circulate air between rooms. So the reason I want to start with this really basic floor plan is because I wanted to point out that although there are, let's see, 1, 2, 3, 4, 5, 6 different rooms or spaces in this really simple floor plan, there is nothing here to indicate that this should be any more than a single drying chamber, right? And I've seen this interpreted literally as 6 or 7 different drying chambers in a drying report. And that was the root and the source of the problems in those cases for some of the drying challenges that those contractors, those restorers were facing, is because they were thinking of all of these as separate drying chambers. And I've literally seen that, even a closet, because it's its own room, that it should be established as its own chamber. And that's definitely inaccurate, right? Now, to really know how many chambers you have, you take an initial guesstimate, right? Just like with class, it's an initial guess. Looking at this floor plan, I see openings between all of these rooms, and those openings are standard door widths. and I can provide ample airflow through a standard door opening. There's no obstruction there that prevents me from doing that. So there's nothing here that would indicate that I have a restriction to my circulation between any of these spaces. And that's what I'm going to look for. Is there an area where there is a reasonable restriction that is going to prevent me from circulating air between two of these rooms, two or more of these rooms? And if I see that, then we are going to have separate chambers as my initial estimate. The other reason in looking at a floor plan like this that I might establish a separate drying chamber is if I have very, very unique and critical needs in one area versus another, right? So, and I may look at it this way, for example, maybe one of these areas, maybe this larger room right here, maybe that area is all hardwood flooring, and it's maybe it's a really high value hardwood flooring. Maybe it's some Brazilian hardwood or something like that, and there's a lot of value per square foot in that floor, and I need to get on it quickly and address it much more aggressively than I would the balance of the space. And maybe the balance of the space is all carpeting, right, over cement or carpeting over a plywood subfloor over a crawl space, whatever it is, but something a bit more typical where I don't necessarily need to be as aggressive or purposeful in the system that I'm going to apply. And in a case like that, I may choose to break the chambers apart so that I can control the spaces independently, right? So that may be another reason that I would break these into separate drying chambers. Now, once I've established my drying chamber, at least my estimate at my drying chamber, and I've established the dehumidification that would be appropriate for that based on my class, et cetera, then the next step in a drying chamber is to validate what a drying chamber is. And that is to obtain, and this is something I've stressed over, a lot of different episodes here in Technically Speaking, because it's so, so important. But what you're going to do is you're going to establish a temperature and humidity value at one extreme of that chamber, one far end of that chamber, and then go to the opposite end of that chamber and take the same measurement. And what you're validating here is that the temperature and humidity are virtually identical, right? I'm not concerned about tenths of a degree and tenths of a percent RH, but if you're any more than about 1 to 2% RH different, any more than about 1 to 2 degrees Fahrenheit different between those two extremes, then your circulation is restricted, right? And you have two choices at that point. I can either modify the way I'm moving air so that I get better circulation, or I can treat them as separate chambers, right? Those are my choices at that point. But what you're going to find is that in a standard floor plan like this, as long as air movement has been established properly, you're not going to find that substantial restriction to airflow. So I want to illustrate that a little bit because it's important. I'm going to indicate just kind of the methodology behind the way this circulation would be established, because there's only one right way to do it. There's only one correct way to get this circulation from room to room. And if this is a principle that you're not real familiar with, then you're probably seeing a lot of disparity in those two temperature and humidity readings across even a standard residential, 2-bedroom home with 40% of it affected, equating out to, 5 or 6 rooms. If this principle that I'm going to show you here is not being applied properly, you're probably seeing some rooms dry much faster than others. One side of your blouse is getting too warm, the other one's getting too humid, and you're not seeing a good mix of the environment across. And this is what that looks like. So I'm going to take an air mover here, and we're going to take a look at it from a top-down view. So here is the top of the air mover. I've got an outlet right here in the front of my air mover. Your air mover has an intake on the side. Your standard carpet dryers have an intake on the side. That side that air comes in is always the left-hand side. It's always the left-hand side. That right-hand side right here is not an intake. That right-hand side is the hubcap of the motor, right? There's a tiny bit of air that goes in there, but that air that goes in is just cooling the motor down. 90% of your air is coming in that left-hand side. I just accidentally changed that, didn't mean to. But 90% of your air is coming in on the left-hand side. Now, because of that, that air mover has to be installed in a very specific direction. The intake drawing from one room and the outlet dropping into the next. All right, you see the direction of flow there? The intake coming from one side and the outlet going into the next. That orientation only works clockwise. When you install your air movement, start by installing your air movement around the perimeter of the room and move your air in a clockwise orientation. Now, your new low profile air movers, technically you could flip them on either side and go counterclockwise if you wanted to. Your axial air movers don't draw from a neighboring room, right? The air goes straight through an axial air mover. So this installation wouldn't necessarily work with an axial air mover. And I'll just draw that in a different color so we can differentiate here. But if I were to use an axial air mover here in one of these, my axial air mover is going to draw from the same room and drop to the same room. It's not going to create that room-to-room circulation. So everywhere you've got these openings between two rooms, the air mover you're going to use here is going to be this type. You're going to use an air mover, whether it's a low profile or it's a standard traditional carpet dryer, so that you can bend that air 90 degrees and draw it from one room and drop it into the next. Now, the rest of your airflow that you use to boost air around a room doesn't really matter what type it is. But at those openings, you've got to use an air mover that will bend that flow. And it's got to be installed in that clockwise direction to make that bend occur. Okay. All right. So once you've done that and you've established that, and every room has a mix with the next, what you're going to find is that you're going to have great circulation to the tune of 1,000 or more cubic feet per minute, because that's the CFM on these air movers, that is blending the air from one end of the chamber to the other. You know, if you were to become a little water molecule and travel along this train all the way along the space based on the speed of this air movement, it would take you, probably about 3 or 4 seconds to make a whole revolution around that entire space at the most. So it's a very, very rapid exchange between two rooms. That'll be reflected in those temperature and humidity readings. So when you take these readings of your temperature and humidity at these locations, if I can get my little cursor to move here, there we go. When you take these two readings, you're going to find significant commonality between these two if you've established that air movement properly. Okay. All right. So that's on a simple floor plan, and some of the reasons I might or might not break my chamber apart in a simple floor plan, and how I may even consider class in the establishment of those drying chambers. Let's take a look at a slightly more complicated floor plan. So in this floor plan, we have a couple of rooms, a couple of spaces that are identically laid out between two. These might be condos or apartments. We have a common wall in between the two apartment units here. And then we have a bathroom area here. We have a kitchen area here that are backed up against each other, like a utility room area here. So something very common that we might see in a single bedroom apartment layout or a single bedroom condo layout. Now, in this scenario, it becomes very obvious that we would have to establish a minimum of 2 drying chambers if both of these units are affected. So let's say we had a water source here and water has leaked out and affected, a substantial amount of this unit, and then it migrated through this wall and has affected a small portion of this unit, right? So these would be 2 completely separate drying chambers, 99 times out of 100. The only reason this wouldn't be 2 entirely separate drying chambers is, let's assume that maybe that leak was a category 3. And if it were a category 3 and had affected this common wall in between the two, I'd probably demo that common wall, right? And as soon as I demo that common wall, I can create airflow and circulation between the two units, okay? Depending upon how that common wall is constructed. And what materials it's comprised of. But most of those materials, especially if there's insulation present and we're dealing with drywall, that wall would have to come down. So apart from that scenario, these would be 2 entirely separate drying chambers. Now, having said that, let's talk a little bit about classification and how I would apply class. In this lower area here, where I've got a much larger portion of my structure actually impacted or affected by water migration, here we're dealing with a much larger overall surface area that is impacted. If I close this room off because it's not affected, and I close this room off because it's not affected, to apply my class of water, I'm going to consider the amount of this area here, and I'll shade this in to be clear, what amount of this area has been impacted as a general percentage, as an approximate percentage. And that's how we establish that classification, is the approximate percentage of the surface area within my drying environment, not of the total space, right? Not of that total space, because I'm excluding this area, but the approximate percentage within my drying environment that I'm trying to control. Secondarily, then, what are my wet surfaces? Where the water exists and will be evaporating from, what are those surfaces? Are they highly porous goods? Or are we dealing with water that's in difficult to dry materials? Is that where my wet surface is? Now, notice that I'm stressing the wet surface because it's an initial evaporation load. I may have some materials that are affected that are lower in permeability, but if I've got wet carpet and wet pad on top of that, and I'm going to save those materials, then initially my evaporation load is going to be pretty high, right? So I'm going to use those wet surfaces that will be contributing to evaporation for that initial evaporation load. From there, we'll make adjustments based on my instrumentation, based on what we see for progress as we move through the project, right? Whereas on the other hand, in this space up here, if this was predominantly a hardwood floor that is impacted up here in the unit that's on the top side of this drawing, this would likely be a class 4, right? Especially if I can contain down to the area that is actually affected and maybe use a temporary barrier so that I'm just dealing with this area. However, it could also be a class 1. If I leave this entirely open and do not construct a temporary barrier, then the percent area affected here could also be considered a very low percentage of this larger area that I'm dealing with. All right. With class 4, what I typically interpret from the S500 is that if we are dealing with only trapped water that is hidden or that is absorbed only in low porosity materials, regardless of the percent area that is affected, I generally treat those as a class 4. And the predominant reason that I do that is because I want to produce very, very low humidity. Not necessarily a high volume of humidity control, but a very low humidity. And there's some good guidance in the S500 for how you establish that lower humidity, especially even with the dehumidifier sizing guidelines and the fact that desiccants become an option in my class 4 environments. All right, and something that is much more accustomed to that class 4 drying. All right. So that's kind of from the high level, taking a look at class and category and applying some of that class and category into some scenarios. The next thing I want to do here is talk a little bit more about the interstitial cavities and voids discussion. This is a schematic that I've put up a couple of times in Technically Speaking, and I like using this because it really illustrates that a building really is a three-dimensional space, and there's a lot more to a structure than what we see, right? So if I'm standing in the middle of this space and I'm looking at this space, what I see are materials, right? I see these materials. What I don't see are all of the materials that comprise the totality of these assemblies. And from a water migration standpoint, when water is moving through the space, water is going to start from wherever this source is, wherever that source is, and migrate across these materials, then absorb into all of these spaces. And as it absorbs into these spaces, I've got to consider, how have I set up my air movement and my drying environment to ensure that the air movement is capturing the water that is inside of all of these cavities and voids? And again, it kind of comes back to that conversation that we had at the very beginning about your instrumentation. The first step in really being able to establish an accurate class and an accurate drying environment or chamber is just making sure that you've actually identified what's wet, right? And the principle that I always stress in helping a technician really ask that question honestly and sincerely and get to the root of the answer is to not think of what you're seeing in a building as assemblies. All right. You got to think about the individual components, right? In other words, a common mistake that I think a lot of us will make, just the human mind kind of simplifying things, is that when I look at a wall, I call it a wall. And that's kind of the habit you've got to break as a restorer. Don't look at the wall and call it a wall. What you're looking at is paint, right? What's behind that? All right. Well, what's behind that is drywall. Well, what's behind that? What's it holding on to? Right? What is it attached to? It's attached to studs. All right. What's between the studs? Is it air? Is it insulation? You've got to think of each one of those components and ensure that you've checked the box that you know what those components are. Right? Only then can I establish the appropriate instrumentation to verify whether or not the moisture has actually affected those materials, right? And we could go through a pretty lengthy discussion on understanding that and then applying the art of tracking water migration, right? And in the simple terms, you have to measure for moisture everywhere that you reasonably expect moisture could exist as you track migration. If I know that the floor is wet at the foot of cabinets in a kitchen, for example, it's reasonable to expect that the floor beneath the cabinets is wet, right? And if the floor beneath the cabinets is wet, it's reasonable to expect that the wall behind the cabinets has also become affected. So now I have to check the wall plate behind the cabinets, the drywall behind the cabinets. If those are impacted, then it's reasonable to expect that the insulation in that cavity is affected. So you kind of follow my line of thinking there. You continue to do that until you find things that are unaffected. And one of the things that I'll always stress is that the moment you find unaffected materials, document it. And those that have been through any training with me before, hopefully you've heard me stress that before. You have to check everything that is reasonable, can be reasonably expected to be wet. You then have to document everything you check. I don't have to measure every material in a building, but I have to measure everything that could reasonably be wet. And then I have to document everything I check. And what I'm stressing there is that if you checked it for a reason, right? You checked it because there was a chance it could have been wet. You found out that it wasn't. Wonderful. Document that, right? There should never be an instance where we've inspected an assembly and then a component in that assembly during that investigation and not documented something and not committed that to the record in some way. Because if I could reasonably argue it could have been wet, so can somebody else 6 months from now when they do a remodel and open that wall cavity and find a bunch of microbial growth, right? And then point their finger back at the drying contractor that handled the project 6 months ago and said, oh, this must have been wet and they missed it. I wonder if the drying contractor is at fault here, right? When in reality, that was there, 10 years prior to there ever being a water event, right? In order to avoid that type of exposure and that type of risk, we, again, check everything that may be wet and document everything that we check. Okay. All right. A little bit of a soapbox there, but I think it was an important one to step on for a moment. Next thing I want to step into here, let's take what we've talked through today and let's apply this against the restoration process. This is a flow chart that I use to kind of bring back a lot of the technical topics that I touch on and center them around what I call the universal restoration process, which are the core things that have to happen on every mitigation project, right? Kind of mapping out the thinking process as we go through a mitigation project. The very first thing that we need to do in a mitigation project is first establish, from a drying perspective at least, obviously you need to greet the customer and all kinds of stuff. But from a drying perspective, we just have to establish what is wet. That's the first question that we need to define. To establish an appropriate scope, I need to know what's wet. What we talked about today that I want to hang on that question is knowing what's wet as we establish class and drying chambers means we have to look beyond the assembly, right? Really understand the importance of the difference between an assembly and a component. Right? Your documentation shouldn't be just at the assembly level. Your documentation should be at the component level. What's the difference? An assembly is a wall. A component is the paint, the gypsum wallboard, the 2x4 stud, the 2x4 plate, and the wall cavity insulation. Those are the components, right? So we have to document at the component level. And if you find in your documentation, I'll give you this as a homework assignment, just go pull some random files out and find out how often as an organization, what you're documenting is a wall is wet or a floor is wet or a ceiling is wet, or even a chair, right? It's not the chair that's wet. Yeah, what component is affected? So document what's wet at the component level, right? That's the key there. Once we know what's wet, conversation for a different day. But next thing we do is what we call the restoration triage, which is evaluating cost, damage, and contamination to determine restorability. Again, had a great episode on that in Technically Speaking yesteryear. In one of our episodes last year, we dug into that conversation. But cost, damage, and contamination. Those will establish, should I restore the material? Possible answer is no. Possible answer is yes, right? What is the restorability? Once we determine that something is indeed restorable, and that we do have restorability, the second question that we have to ask is how wet? Now, notice I haven't even established class of water yet, right? Because both of these inputs are really necessary to establishing that class. Where is my water? How deeply absorbed is it? Are we talking about just wet surfaces? Are those wet surfaces highly porous materials? Where does that water really exist within my structure? Documenting how wet means that I need numbers. Right, and this is another area that we could spend a lot of time really expanding on the critical nature of just how important this is, but I'll just share with you for a moment. one of the common mistakes that I think we make as an industry a lot, and that is going out to a project on day one, establishing that an area within a room is wet and affected. It's obvious because I see pools of standing water. We extract, right? We place our drying equipment, and nobody bothers to break out a moisture meter because it's obvious, right? The floor is wet and had a puddle on it, right? A big old puddle right in the middle of the room. So nobody breaks out a moisture meter and tracks a number. Well, that puddle was extracted. The puddle isn't what's wet. What's wet is the absorption that occurred into the materials that were beneath that puddle, right? And if I don't establish a number on day one, whatever that number is, then when I come back the next day, I don't know what the next day's number means to me, right? If you go into a project on day two and you get a 90, whatever that 90 represents, right? We could talk about that for a while too, but we won't. But whatever that 90 represents, if I don't have a reference point from the prior day that says it was 90 yesterday, then I'm not aware of the fact that I'm not making drying progress. I mean, just how ludicrous is that as from a drying perspective, right? Now, if it was 100 yesterday and 90 today, I know I'm making progress, right? If it was 100 yesterday and 50 today, I know I'm making phenomenal progress. But even if I get 40 on day two, which may sound great compared to the numbers we just discussed, if it was 35 on day one, that's bad news, right? So it's really critical that we don't overlook that. And I think it's one of the things that we commonly do as an industry that is as a habit that we need to break, is that you have to have a quantification of how wet materials are on that first day. Now, once I know what is wet and I know how wet those materials are, then I can establish my drying plan. And your drying plan is going to include your class of water. Sorry for the horrible penmanship today, but that's going to establish your class of water. That's where you're going to then, based on that class of water, establish the dehumidification plan that you're going to deploy, how you're going to erect your chambers, et cetera. That's where the drying plan comes into place. And that's the kind of the thinking process of day one, if you will, of the mitigation effort. The rest of this all comes in on day 2, 3, 4 through completion of the project. So I just want to kind of hang those a little bit into that restoration process and kind of show where those line up into that mitigation process. So with that, quick reminder, I want to thank you to Chris, Tom, James, and Anonymous for the questions that you've posted into the Q&A. I'm going to come on to those questions in the Q&A here in just a moment. So if you have a question and you haven't logged it yet, please do so. But before I do that, let me just really quickly talk about what's in store for you for season 3. So a real quick look at the lineup here for this year. First of all, one of the key things I'm going to zero in on this year is the fact that we have a number of new standards either about to drop or that have dropped here in the last couple of months. And we're going to spend a lot of time talking through those new standards this year. So S700 is a big one. That's the new fire restoration. Well, I should say new because it's not quite out yet, but it's very, very close. The S700 structural fire restoration standard have a phenomenal consensus body that has been working on that document over the course of the last several years. Some folks that have been just near and dear friends of mine in industry for a long time, and a lot of just experts in that area that have just been really grueling over that document. So I'm excited to bring some of those folks into Technically Speaking and talk a little bit about the fire standard. That'll be on the calendar for this year. Another document that just dropped here late last year is the HVAC assessment standard. Very commonly, especially for some of you, depending on where you are geographically, we encounter affected HVAC systems, heating, ventilating, and air conditioning systems. And a lot of conversation about, should I run them? Should I not run them during the drying process? What should I do if the ducting is impacted by water, especially if it's rigid ducting, if it's rigid insulation line ducting, if it's flex duct, et cetera, et cetera, et cetera. So I'll bring in some experts in that area this year, and we'll talk a little bit about just the role of an HVAC system and kind of its impact on the restoration effort. And then the S520 is about ready to re-release an update into its document, and we'll bring in some of the expertise that participated in that standard as well, and talk a little bit about those. And of course, my core, my home, what I love, water damage. We'll talk lots about water damage this year, lots and lots about water damage. So anytime you got ideas on what you want in the lineup, by the way, please do shoot me an email at brburton@corelogic.com. That's how you can reach out to me directly if you've got anything you want to make sure gets into the repertoire.